Name of this presentation is Introduction to Populations, so please write that as a heading in your notebook. We're going to start with is what a definition of a population is. So you're going to want to write this down as well. Population definition is a group of organisms of the same species living in the same geographical area. So the pictures that I have here represent populations. There's a population of ladybugs here. Okay, here's our population of ladybugs. It's a population of tulips here. Okay, so they are living organisms, they're the same species, and they're in the same area. All of those things tell us it's a population. What we are interested in this class is how populations grow over time. So you don't need to write this down, but this is kind of the direction we're going to take this in class, is to see how can these populations change over time. For example, the size of the white-tailed deer population is used to make decisions about hunting permits. So there's probably a lot of you out there that are interested in hunting or have gone hunting before, or just we know about hunting season in Minnesota. We have to estimate what the population of the deer is, the deer herd in Minnesota is each year, in order to figure out how many hunting permits we're going to give out, how many different types of hunting permits we're going to give out, doe permits and things like that. So population growth, what we see changing in that population over time, is really important to a lot of the decisions that are made on a daily basis. Okay, so what we're going to talk about then in discussing population growth is variables in a population. So please write that as your heading for the next section. Variables in a population would mean what kinds of things can either increase, and that's what this plus sign is for, or decrease, and that's the minus sign, the growth of a population. So we'll start with the increases. Two things can increase a population's growth. Immigration, which is new organisms moving in. So I'll just write that down for you. New organisms moving in. And births is pretty self-explanatory. So the organisms that are already there are having new births or reproducing. On the opposite side of that are the things that can decrease the population. Emigration, which is the opposite of immigration, is organisms moving out. Leaving the population. So from moving from one area to another as far as the geographical location goes. Also, obviously, deaths can decrease the population. For whatever reason they may die, it's going to decrease the overall population. Okay, so that's pretty straightforward. Two things can increase our population, two things can decrease our population, but there are a lot of factors that cause more births or more immigration, and factors that cause more immigration or more deaths. So we need to look at those factors next. Alright, the first type of population growth that things fall into is called exponential growth. Do you write this heading and an abbreviated definition of this. Okay, so exponential growth is a type of population growth in which each new generation is double that of the previous generation. So each new generation doubles that of the previous. Okay, so basically the population is growing faster and faster and faster and have an unlimited increasing rate of growth. What this means then, in order to get this rate of growth, is that births and immigration are pluses, have to be greater than deaths and emigration are minuses. Okay, that makes sense. So our pluses add up to more than our minuses. So just so you don't forget, births are a plus, immigration is a plus, deaths are a minus, emigration are a minus, or is a minus. So an example of when this might actually happen is in bacterial growth. So there's a little picture of bacteria there. Bacteria grow very rapidly as far as their reproductive rate goes, and so they reproduce more quickly usually than they die. Also, the movement in and out of the population is pretty limited, so immigration and emigration is usually pretty limited. So their population growth rate is going to keep increasing faster and faster and faster as long as they have all the resources they need. This is continued on with exponential growth. In exponential growth, there are no limiting factors, and we'll get back to that in a little bit, what those mean, but basically there's other things that are in the environment that can slow down the growth rate. So we'll just add that on real quick. So, oops. Slow, I'm going to abbreviate GR, the growth rate. Also, no individuals are dying and all are reproducing. Again, this is very characteristic of bacteria. They can reproduce really easily because they just reproduce by splitting in half. They don't have to be a certain age to reproduce. And they can reproduce faster than they actually die. When you graph these populations, these exponential populations, they result in what's called a J curve. Now, it's not a perfect J, but let's just give you an idea what this might look like. So in a J curve, this is our graph of time, and over here is the number of organisms. Each section of time or segment of time, remember, the growth rate is doubled. So we start off a little bit slowly, but our graph gets higher and higher and higher in slope. And that's supposed to represent kind of a J there. The hook down at the bottom isn't great, but it gives you that idea. The population just keeps growing and growing and growing at a faster and faster rate. And so this slope is getting steeper and steeper as time goes on. Some other characteristics are, this is typical of new environments, or if we have an invasive species. So if a beetle, for example, like the Asian beetle, comes into a new environment where it doesn't have many predators or doesn't have a lot of competition, has lots of food, we'll often see this exponential growth or this J curve. Invasive species, the same way. You know, they're coming into an environment where they don't have a lot of competition, kind of like our Asian carp. Also rebounding from a catastrophic event. So let's say after there's a big flood or something, organisms that are well adapted to that you know now don't have much competition because everything's been wiped out, but they have the resources they need, will grow like crazy. Kind of like those giant ragweed that are down by the trail. They really do well after a flood because their seeds are dispersed through the flood and they don't have much competitors. Again, the Asian carp is a prime example of this. Okay, it's an invasive species coming into a new environment. Nothing eats it. It doesn't have any predators. It's got lots of food in the algae, and it's just growing like crazy in that exponential growth pattern.